Well, hello again. Today we're going to take a look at something that has been written up in the other writings, so you've maybe glossed over it. I want to make sure that everyone understands this topic because it is huge in technology. This topic or this concept I call shrinking it down. The ability to take what you're doing within a computer system and make that smaller and smaller and smaller. So in a little history, I talk about how we start with these vacuum tubes, and those vacuum tubes are basically representing a 1 or a 0. Again, that's an oversimplification of the process, but it's a 1 or a 0. And the first vacuum tubes were really big. They were huge. You can look at pictures of them. They're massive. I have a vacuum tube. Some of them are quite expensive these days. And so I have a vacuum tube that's a little cheaper, and it's about that big. And then we go to transistors here. So I put on the screen when vacuum tubes 1904. So we're looking at vacuum tubes actually being put into ENIAC, right, in the 40s, 1940s. Well, this transistor had already been made, but it had not been perfected to the level it needed to be. And basically that transistor is the same thing as a vacuum tube. So you're going from the one I have, which is this size, down to the one that I have that's this size, right? That's really small. So you're talking about shrinking that down to 40 times, 60 times smaller than the vacuum tube. And that really enables systems to go from these large, massive computers with not a whole lot of power compared to what we have today, using a lot of power, but not having a lot of computing power, to something that now we can put into the size of a refrigerator, or maybe one wall. One wall is that computer instead of a whole room is that computer, or one size of a mini fridge is that computer. And really making things much more powerful with these transistors doing the same thing as vacuum tubes. Well, then integrated circuits, as I mentioned, they're invented in 1958, and you can put up to 1,000 transistors into a chip that's as big as one finger. So you got a chip and it's got thousands of these transistors on it. Now, all that is just a massive oversimplification because by the time you get to integrated circuits, you're talking about not having to wire how you code things. Like if we send this over here, it will do this thing. If we send the signal this way, it'll do this thing. And being able to actually have that just into a chip. And then finally, we get to our microprocessor chips, which is really an integrated circuit. That's what it is, and putting millions of them on there. Now, I mentioned this before, so I'm just going to pull this up in correlation to this, or maybe you haven't watched this video yet. I'm not sure. And if we look at the Apple M1, and they won't be the only ones to do this. I don't know why the industry allowed them to be the first one to do it. Processor. Sometimes I just don't get what I'm looking for. Yeah, it's in these little tiny machines, but there's, again, this picture of the M1, and it's got 16 billion transistors on this, what we would call a processor, onto a CPU. Now you'll notice that this one is actually showing you it's got 8 cores of a GPU because graphics has become so big of a deal, and 8 cores of a CPU, which is really what most of us would call this whole thing instead of saying it's a processor. And then a neural engine with 16 cores, in other words, the AI stuff. And it's using a 5 nanometer process. And I might as well just throw this in. The nanometer means how small are these circuits. So even from the time that we really began this situation, here we are, and this isn't one of the older ones, but even since then, we've gone from like 11 nanometer down to 5 nanometer. And there's only so much we can do with that. But when you, again, that's shrinking it down, when you make all that stuff closer together, that's a huge difference. Remember that an electron is very small. And so traveling across a bigger area takes more time. And shrinking that down into a smaller area takes less time. And that really does affect things on the nanometer. That's why they always put that on the fact sheets basically for processors these days. So understand that we wouldn't have the notebook computers we have. We would not have our cell phones, our smartphones, because we wouldn't have any way to put this into it. It would not have the computing power we need. It would take too much voltage to do, and it would be too big for us to actually worry about. So the shrinking it down has made things more powerful and cheaper. And as we continue to shrink things down, that will give us even more and more power. That's why Microsoft, in one of the videos that you'll watch later, is thinking that you're going to have smart glasses. That's what you'll have. And maybe you'll have a smartphone still. Maybe that'll be a choice, or maybe people will just go for the glasses. And being able to put processors into these and having them so power efficient that you could run those glasses and talk to them and have augmented reality in front of you and share that augmented reality with somebody else. The only way that can happen is if the shrinking down process continues to occur. Being able to put more and more computing power into a smaller and smaller space. Quantum computing is part of that, just to mention. Quantum computing may be the fourth wave of computing, and that is shrinking it down to the size of an atom. And yes, it's already there. IBM, you can already rent time on their quantum computing. So Google tends to get their name out there a lot, and people go, oh, Google's doing that. And that is true, but above them are about 5 other companies that have been working on it for quite a few years. The problem with quantum computing, you can go and look, type in quantum computer and look at the pictures of them. You'll notice that they look really weird, but that's okay, right? Our ancestors of our PC looked really weird. The difference here is that you're dealing with a limit of science. And currently that limit is, how can you get quantum computing to an actual room temperature situation? So quantum computing is already having an effect. It will continue to have an effect, but whether or not we'll be carrying around that kind of power in our pocket will depend on whether or not they can get that technology to room temperature. What I mean is, if you want to make a 1 or a 0, then you have electricity or no electricity. You have radio wave, no radio wave, light, no light. Right, you can make a 1 and a 0. Quantum computing, you would have to do the same thing, even though if you read up on it, it's got more than 2 states. But quantum computing has to replicate those states of being for that molecule every single time. There cannot be an error. You cannot have a situation where it doesn't represent the 4 states that it represents, or the 3 states that it represents, or the 2 states. It has to be there. It can't just all of a sudden go, oh, whoops, didn't compute that time, sorry. And so right now, they've been able to raise the temperature, but we're still well below 0 to make quantum computing happen. And so they will have to overcome that in order to make it a reality for, say, a watch or a phone or glasses. If that ever happens, oh boy, heaven help us. I don't know what kind of computing we're going to do with that. There definitely is a lot of power in quantum computing, because again, you are shrinking things down so small, you can't see the computer unless you have an electron microscope. So that's something right there. Anyway, if you got comments or questions on that, let me know. I'll help you out where I can.